Section 13.5, Colligative Properties. Some physical properties of solutions differ in important ways from those of the pure solvent. For example, pure water freezes at 0 degrees Celsius, but aqueous solutions freeze at lower temperatures. Ethylene glycol is added to the water in radiators of cars as an antifreeze to lower the freezing point of the solution. It also raises the boiling point of the solution above that of pure water, making it possible to operate the engine at higher temperature. The lowering of the freezing point and the raising of the boiling point are physical properties of solution that depend upon the quantity or concentration, but not the kind or identity of the solute particles. Such properties are called colligative properties. Colligative means depending upon the collection. Colligative properties depend on the collective effect of the number of solute particles. In addition to the decrease in freezing point and the increase in boiling point, vapor pressure reduction and osmotic pressure are colligative properties. As we examine each of these, notice how the concentration of the solute affects the property relative to that of the pure solvent. Lowering the vapor pressure. We learned in section 11.5 that a liquid in a closed container will establish equilibrium with its vapor. When that equilibrium is reached, the pressure exerted by the vapor is called the vapor pressure. A substance that has no measurable vapor pressure is non-volatile, whereas one that exhibits a vapor pressure is volatile. When we compare the vapor pressure of various solvents with those of their solutions, we find that adding a non-volatile solute to a solvent always lowers the vapor pressure. This effect is illustrated in figure 1320. The extent to which a non-volatile solute lowers the vapor pressure is proportional to its concentration. This relationship is expressed by Raoult's law, which states that the partial pressure exerted by a solvent vapor above the solution, P sub A, equals the product of the mole fraction of the solvent in the solution, X sub A, times the vapor pressure of the pure solvent, P naught sub A. For example, the vapor pressure of water is 17.5 torr at 20 Celsius. Imagine holding the temperature constant while adding glucose to the water so that the resulting solution has a partial pressure of water of 0.8 and a glucose partial pressure of 0.2. According to equation 1310, the vapor pressure of water over the solution will be 80% of that of pure water. In other words, the presence of the non-voluble solute lowers the vapor pressure of the volatile solvent by 17.5 torr minus 14 torr equals 3.5 torr. Raoult's law predicts that when we increase the mole fraction of a non-volatile solute particle in a solution, the vapor pressure over the solution will be reduced. In fact, the reduction of vapor pressure depends on the total concentration of solute particles, regardless of whether they are molecules or ions. Remember that vapor pressure lowering is a colligative property, so it depends on the concentration of solute particles, but not upon their kind. Figure 1320, vapor pressure lowering. The vapor pressure over a solution is formed by a volatile solvent and a non-volatile solute. It is lower than that of the solvent alone. The extent of the decrease of the vapor pressure upon the addition of the solute depends on the concentration of the solute. An ideal gas obeys the ideal gas equation of section 10.4, and an ideal solution obeys Raoult's law. Real solutions best approximate ideal behavior when the solute concentration is low and when the solute and solvent have similar molecular sizes and similar types of intermolecular attractions. Many solutions do not obey Raoult's law exactly. They are not ideal solutions. If the intermolecular forces between solvent and solute are weaker than those between solvent and between solute and solute, then the vapor pressure tends to be greater than that predicted by Raoult's law. Conversely, when the interactions between solute and solvent are exceptionally strong, as might be the case when hydrogen bonding exists, the vapor pressure is lower than Raoult's law predicts. Although you should be aware that these departures from the ideal solution occur, we'll ignore them for the remainder of the chapter. Boiling point elevation. In sections 11.5 and 11.6, we examined the vapor pressure of pure substances and how they can be used to construct phase diagrams. How will the phase diagram of a solution, and hence its boiling and freezing points, differ from those of a pure solvent? The addition of non-volatile solute lowers the vapor pressure of the solution. Thus, as shown in Figure 13.22, the vapor pressure curves of the solution, which are the blue lines, is shifted downwards relative to the vapor pressure curve of the pure liquid, which is the black line. At any given temperature, the vapor pressure of the solution is lower than that of the pure liquid. Recall that the normal boiling point of a liquid is the temperature at which its vapor pressure equals 1 atmosphere. At the normal boiling point of a pure liquid, the vapor pressure of the solution will be less than an atmosphere. Therefore, a higher temperature is required to attain a vapor pressure of 1 atmosphere. Thus, the boiling point of the solution is higher than that of the pure liquid. The increase in boiling point relative to that of the pure solvent, delta T sub B, is a positive quantity obtained by subtracting the boiling point of the pure solvent from the boiling point of the solution. The value of delta T sub B is directly proportional to the concentration of the solution expressed by its molality. The change in temperature of the boiling point, depression, is equal to a constant times its molality. Figure 13.22. Phase diagrams for a pure solvent and for a solution of a non-voluble solute. The vapor pressure of a solid solvent is unaffected by the presence of a solute if the solid freezes out without containing a significant concentration of the solute, as is usually the case. Freezing point depression. When a solution freezes, crystals of pure solvent usually separate out. Solute molecules are not normally soluble in the solid phase of a solvent. When aqueous solutions are partially frozen, for example, the solid that separates out is almost always pure ice. As a result, the part of the phase diagram in Figure 13.22 that represents the vapor pressure of the solid is the same as that for the pure liquid. The vapor pressure curves for the liquid and solid phases meet at the triple point. In Figure 13.22, we see that the triple point for the solution must be at a lower temperature than that of the pure liquid because the solution has a lower vapor pressure than the pure liquid. The freezing point of a solution is the temperature at which the first crystals of pure solvent began to form in equilibrium with the solution. Recall from section 11.6 that the line representing the solid-liquid equilibrium rises nearly vertically from the triple point. Because the triple point temperature of the solution is lower than that of the pure liquid, the freezing point of the solution is lower than that of the pure liquid. The decrease in freezing point is a positive quantity obtained from subtracting the freezing point of the solution from the freezing point of its pure solvent. Like the boiling point elevation, delta T sub F is directly proportional to the molality of the solute. The values of K sub F, the molal freezing point depression constant, for several common solvents are given in Table 13.4. For water, K sub F is 1.86 Celsius, and therefore 1 molar aqueous solution of sucrose or any other aqueous solution that's 1 molar in non-volatile solute particles, such as 0.5 molal sodium chloride, will freeze 1.86 degrees Celsius lower than pure water. The freezing point lowering caused by solutes explains the use of antifreeze in cars and the use of calcium chloride to melt ice on roads during winter. Osmosis. Certain materials, including many membranes in biological systems and synthetic substances such as cellophane, are semi-permeable. When in contact with a solution, they allow some molecules to pass through their network of tiny pores, but not others. Most importantly, semi-permeable membranes generally allow small solvent molecules, such as water, to pass through, but block out larger solute molecules or ions. This selectively gives rise to some interesting and important applications. Consider a situation in which only solvent molecules are able to pass through a membrane. If such a membrane is placed between two solutions of different concentration, solvent molecules move in both directions through the membrane. The concentration of solvent is higher in the solution containing less solute. However, so the rate at which the solvent passes from the less concentrated or lower solute concentration to the more concentrated solution, which is higher solute concentration, is greater than the rate in the opposite direction. Thus, there is a net movement of solvent molecules from the less concentrated solution into the more concentrated one. In this process, called osmosis, the net movement of solvent is always towards the solution with the higher solute concentration. Osmosis is illustrated in Figure 13.23. Let's begin with two solutions of different concentrations separated by a semipermeable membrane. Because the solution on the left is more concentrated than that one on the right, there is a net movement of the solvent through the membrane from right to left, as if the solutions were driven to attain equal concentrations. As a result, the liquid levels in the two arms become unequal. Eventually, the pressure difference resulting from the unequal heights in the liquid in the two arms becomes so large that the net flow of solvent ceases, as shown in the center panel. Alternatively, we may apply pressure to the left arm of the apparatus, as shown in the panel on the right, to halt the flow of the solvent. The pressure required to prevent osmosis by pure solvent is the osmotic pressure, pi, of the solution. The osmotic pressure obeys a law similar to that of the ideal gas law. Pi volume equals nRT, where V is the volume of the solution, N is the number of moles of solute, R is the ideal gas constant, and T is the temperature in Kelvin scale. From this equation, we can write pi equals mRT, where m is the molarity of the solution. If two solutions are of identical osmotic pressure are separated by a semipermeable membrane, no osmosis will occur. The two solutions are isotonic. If the one solution of lower osmotic pressure, it is hypotonic with respect to the more concentrated solution. The more concentrated solution is hypertonic with respect to the dilute solution. Osmosis plays a very important role in living systems. The membranes in red blood cells, for example, are semipermeable. Placing a red blood cell in a solution that's hypertonic relative to intracellular solution, the solution within the cells, causes water to move out of the cell, as shown in Figure 13.24. This causes the cell to shrivel, a process called crenation. Placing a cell in a solution that's hypotonic relative to the inner cell fluid causes water to move into the cell, as illustrated in Figure 13.24b. This causes the cell to rupture, a process called hemolysis. People who need body fluids or nutrients replaced but cannot be fed orally are given solutions by IV infusion, which feeds nutrients directly into the veins. To prevent crenation or hemolysis of red blood cells, the IV solutions must be isotonic with the intracellular fluids of the cells. There are many interesting biological examples of osmosis. A cucumber placed in a concentrated brine solution loses water via osmosis and shrivels into a pickle. If a carrot that has become limp because of water loss to the atmosphere is placed in water, the water moves into the carrot through osmosis, making it firm once again. People who eat a lot of salty food retain water in tissue cells and intracellular space because of osmosis. The resulting swelling or puffiness is called edema. Water moves from the soil into the plant roots and subsequently into the upper portion of the plant, at least in part because of osmosis. Bacteria on salted meat or candied fruit lose water through osmosis, shrivel, and die, thus preserving the food. The movement of a substance from an area where its concentration is high to that where it is low is spontaneous. Biological cells transport water and other select materials through their membranes, permitting nutrients to enter and waste materials to exit. In some cases, substances may be moved across the cell membrane from an area of low concentration to one of high concentration. This movement, called active transport, is not spontaneous, so cells must expend energy to do it. Determination of molar mass. The colligative properties of solutions provide a useful means of experimentally determining molar mass. Any of the four colligative properties can be used, as shown in samples exercises 1312 and 1313.